So today we are ready to do the second section of Chapter 7. The first section, 7.1, was all about, what was that about? Sampling distributions of sample statistics, but in particular, which one? Sample proportion, right? So sampling distributions, last time we did sample proportion. So just a real quick review of that. Sample proportions, what was the mean of all possible values for a sample proportion? What was the mean of that? Another way of saying this is, where is that distribution, the sampling distribution for p hat, where's it centered? It's at p, which is, what is that notation for? That's the population proportion. When you're dealing with the binomial variable, you can also think of that p as being the probability of success on a single trial. So think about taking a random sample of 50 people from some population and asking them their opinion on some yes or no question. So the population proportion of people who will say yes is p. Or you can think of it as the probability that a randomly selected person will say yes. It means the same thing. All right, now what was the standard error of p hat? That's exactly right. That's the interpretation. But what's the formula for it first?
Square root of p times 1 minus p over n.
Right, good. So the square root of p times 1 minus p over n. Right? Now, what was the shape of that distribution? And remember we used the applet and we did some simulations and we showed that for different binary values for this p, we did a 0.1, we did a 0.2, we did a 0.5. For different values of it, as long as we got the sample big enough, what did that distribution look like? Tall and skinny and very bell-shaped and symmetrical, right? So it had a normal distribution. It was centered at p, and it had a standard error. That distance was the standard error of p hat, and it followed that formula. Now the fact that n is in there on the bottom of a fraction means that as n gets bigger, the value of the standard error gets smaller. Which, you make the standard error smaller, it always takes you to about halfway down the hill. So if I make that number smaller, then I got to make my hill steeper. So I get a skinnier distribution. Intuitively, what that means to a researcher is, if I take a bigger sample, then I force my sample estimate to get closer to the true value, the thing I'm trying to estimate. I don't know what the population proportion of people who will say yes is, but I know if I take a big enough sample, my sample estimate will be real close to it. Okay? So that's a sampling distribution. It tells you the distribution of possible values of that summary statistic instead of distribution of individuals from the population. Okay? Now, someone was in my office earlier today with a question on one of the homework problems, and it said to give the population distribution, the data distribution, and the sampling distribution of p hat. So those three distributions. Well, when you have a binary variable, a binomial variable, what's the population and the data distribution look like? Hint, they don't look anything like a bell-shaped curve. In fact, it's discrete, isn't it? The data distribution means, what's the distribution of data values you get back from individuals? Well, if I have individuals and I'm asking them a yes-no question, in my data set I might code a no as a 0 and a yes as a 1. So what would my distribution look like? Well, I'm going to have 0 and I'm going to have 1 as my only two possible values. The bar that I draw above each of those is just going to be the height of those probabilities. So when they ask you, and one of the online homework questions does this, but at least they do it as multiple choice, so you see what, you don't have to come up with it from scratch, but you'll get a bar. So this 0 means no, or more generically, 0 means failure, 1 means success. It's just proportion of successes. So the height of this thing is p, and let's say that was 0.55. The height of this one is 1 minus p, which is 0.45. And that's going to be your data distribution. If in your sample you got 55% successes, there's your data distribution. The sampling distribution of p hat, though, looks like this. All of the possible values you could get for p hat form a nice, smooth, normal distribution. So today, in section 7.2, we're ready to have the same discussion, but in terms of the sample mean instead of the sample proportion. All right? So let's think about this. On the screen here, I have the distribution that you've seen already this semester from your pulse data. It looks reasonably bell-shaped and symmetric. It's centered at a little less than 72. It's centered at about 71 point something. And I'll show you what that statistic is in just a second. Is this a population distribution, a data distribution, or a sampling distribution? I've heard two of the three so far. And I actually have heard the right one. I heard sampling distribution. No, this is not a sampling distribution. This is a distribution of individual pulses. Okay? This is a data distribution. Right? It's not a population distribution. Population distribution would look a lot like this, only it would be a distribution from the entire population, which you can never actually see. So just the very fact that I graphed the darn thing tells you, oh, it must be a data distribution. Right? But for today's discussion, we're going to pretend like this is a population distribution. In other words, I've got 385 pulses that you guys gave me, and I'm going to treat those as if they are the entire population, and then you gave me a sample of size 5 out of that population. Okay? So now let's talk about your samples of size 5. From your sample of size 5, do you happen to remember what your 5 pulses were? You didn't memorize them? Darn it. Each of you could compute the mean of those 5, right? So if Amy computes the mean of her 5 and Delaney computes the mean of her 5, will they have the same number? No? Why not? Okay, it's a small sample. And did you use the same 5 people she used? No. We're supposed to, right? Since they have different people, they're going to have different pulses, right? It's highly unlikely that anybody has exactly the same sample mean as anybody else, which tells us what? It tells us that the sample mean, x bar, must have a distribution. Pulses have a distribution, individuals, but those sample means must also have a distribution. Remember what a sampling distribution gives us? All the values that are possible and how likely each of those values are. Now, what do you think is most likely for a sample mean of 5 pulses? You think it's most likely to get a mean that's close to the middle or far away from the middle? Close to the middle. So if it's more likely to get close to the middle, then the distribution ought to be taller near the middle, and then get smaller as you move out from that. So you're going to get a nice bell-shaped distribution again. Right? Now, think about spread of the distribution. If I graph, and I will in the next picture, if I graph the histogram of the 77 X bars that I computed from your 77 samples that you sent me, if I draw that histogram, how is it going to look compared to this one?
Narrow,
Narrower? I agree. But why?
Because if the mean is an average, you probably aren't going to have an average of 100 or 52.
Okay? You looked up here and you said, okay, there's 104, right? That's the maximum value in this sample. We're not going to have somebody that gave me a sample that has a mean of 104 if the max is 104. What's the only way we could possibly get a mean of 5 pulses to be 104 if the max in the data set is 104?
there's a lot of them.
Yeah, if all 5 in one sample are 104, then the mean would be 104. But clearly that's not going to happen because this bar isn't tall enough to even have had 5 of them total, right? So there's no way we're going to get all 5 from a sample to be 104 or all 5 to be 42. So the mean, there's one person here who had a pulse of 42. What's the mean of that sample? That person's going to get averaged in with 4 other people. Where's the mean of that sample going to go? What'd you say? Okay, but relative to 42, where's the mean of that sample going to be? Is it going to be bigger than 42? Is it going to be 42 or is it going to be less than 42? It's got to be bigger than 42. It's got to go that way. And the mean of the sample that this person was in has to go this way. So they call that regression to the mean, right? Samples of people will tend to regress toward the overall population mean more than individuals do. Right? So here it is. If I hit page down, I've got the histogram of the 77 means, and I wasn't smart enough, unfortunately, in advance to make this have the same scale on the y-axis. The previous one stopped at 108, this one stops at 124, and so it sort of artificially makes it look even skinnier than it is. But you can still get the point that it's a lot skinnier distribution. See that? Some computer animation for you. The distribution for samples of size 5, the mean of samples of size 5, is very symmetric and bell-shaped. It's got this odd spike right there. It's kind of interesting. That's at 62 beats a minute. I don't have an explanation for that, other than we're dealing with finite number of samples here, 77 samples, and you expect a few oddities like that. But other than that spike, you really get a nice bell-shaped distribution to this thing, and the spread is less than the spread for individuals. Now, put your intuition caps on. Suppose I had asked you to take samples of size 10 instead of samples of size 5. What would that distribution look like compared to this one? It'd be even skinnier. Because then this person that had 42, which is right here, the person who had 42 now gets averaged in with 9 people instead of 4 people, and they're going to get pulled in even closer to the overall average. If you have random samples, then you expect to get roughly equal the amount of variability that there is in the population, and you should get a person with a high value to offset anybody with a small value, and they'll tend to average out and be close to the middle. So intuitively, what happens as the sample size gets bigger? The spread gets smaller and smaller and smaller, just like we saw it do with proportions, which tells us that the standard error of a sample mean ought to have an n in it, right? It needs to be a function of the sample size, because as the sample size goes up, the error goes down. So I need to have a relationship where as n gets bigger, the value gets smaller. Where does the n need to be in that function? It needs to be on the bottom of a fraction. Right? It turns out it's similar to what it is for proportions guess I can go ahead and erase this. I'll just reuse that space. The mean of x bars, the average value of all the possible x bars you could get, is mu. And I'm going to go ahead and put a little subscript of x on there without the bar on it. I'll let you stare at that for a while until you can figure out, well, what does that say in English? Tanner, what does that say in English? See, I set you up for a joke there. You could have said, I don't know, it's Greek to me. Greek letters, right? What does mu sub x bar mean?
Mean of the individual.
No, of x bar.
Oh, I mean
The mean of all the possible values of x bar, right? So that's another way to say this is the center of the sampling distribution of x bar will be at the mean of all the individuals, right? So the mean of the x bar distribution will be at the individual mean value. So mean of individuals. Another way to say that is it's the population mean. Okay? Now to illustrate that, here are the summary statistics for the 385 pulse values that you sent in. The overall mean is 71.667. Okay? I'll hit page down, and there are the summary statistics of the 77 samples of size 5 that you sent in. Look at the mean. 71.6166. The same exact number. Okay? So this is true. The mean of the means is the population mean. Another way to say it is the sampling distribution for x bar will be centered at the population mean. And that's another one of those moments where you should think, oh, thank goodness. What did we say that implies? That the estimator x bar is, I had a word for that?
Unbiased?
Unbiased, good. It's an unbiased estimate of the population mean. So in other words, if I ask you, hey, I need you to go do some research for me, I want you to estimate for me the average pulse of adults. What's the average resting pulse? Immediately you should think, oh, I need to take a sample and compute the sample mean and use that as my estimate of the population mean. Almost always, when you want to estimate something about the population, you collect a sample and compute that thing from the sample, and that'll be your estimate. Right? If it's an unbiased estimate, then on average, it'll come out right. So the average of all the x bars. That's not saying in any one sample you're going to get it exactly right. The sampling distribution tells me that, well, it'll be centered at the population mean, but it's possible to get values that vary from that. But the further away you get, the less likely it is. So if you want to be sure that you get close, what do? Use a big sample. Exactly. If you want to be certain that you get an estimate, x bar, that's close to the population value, then you use a really big sample and you shrink this sampling distribution in until it's really skinny, right around that mu. You force the value of your sample statistic to get close to the true value by taking a big sample. So that standard error of x bar is sigma sub x divided by the square root of n. You had a square root of n on the bottom of the p hat standard error that we had up here a minute ago. Same thing applies for means. It's, what is this sigma x? This is lowercase sigma. What does that stand for? Standard deviation of, and it's a sigma, so it's the population. So I'm going to write it in words. This is the population standard deviation divided by the square root of the sample size. Okay? Now, let's look at those standard deviations. The standard deviation of my population of 385 pulses is 10.315. Right? So I just took the standard deviation of the 385 and I got 10.315. If I divide that by the square root of the sample size, I should get the standard error for sample means, which is also, another way to think of that is it's the standard deviation of all the possible values of x bar that you could get back. It's the spread in that distribution. So what do I divide by? What?
385?
Square root of 385?
Bet your sample size, or 5.
It is either 385 or 5, or it might be 77.
Well, is it population?
Which is it?
Your population is the 385 then, so your sample is 5.
It is 5. And just like in my previous class, I got all three of those answers. 385, no, 77, no, it's 5. Think about it. This is the sample size of the sample from which that x bar was computed. So I'm wanting to know, my x bars are all of samples of size 5 that you sent in. And then I computed the distribution of all of those. And there were 77 of them, but 77 isn't the sample size, and neither is 385 in this discussion where I'm saying those 385 are my population. Okay? So do that for me on your calculator. I'll do it in my head and see what you get. Is that right? I wasn't sure about that last digit, but no, I remembered the number from earlier this morning when I did this. So the standard deviation of the x bars should be about 4.6, right? And when I page down the summary statistics for the 77 that we actually got was 6.54, a little too big, right? But still, it's kind of in the magnitude of where you would expect it to be. Now, why is it a little bit too big? Well, there's a couple of reasons for that, some of which I want to save part of that discussion for a little bit later in the semester. But part of it is we're only looking at 77 x bars. So I have a fairly limited number that I'm looking at, where this is the theoretical standard error from all possible x bars. Okay? Now, even if my population only has 385 things in it, how many possible samples of size 5 could you draw from 385? You should know how to do that by now. That's combinations of 385 things taken 5 at a time. Now, I don't know how many that is, and your calculator could do it for you unless you get an overflow error, but it's a big number. Right? It's probably several million possible samples, of which I got 77 of them. Right? So part of this being off a little from that one doesn't concern me because, well, I only looked at 77 and I got that 6.5, right? Did you get that number?
No, I don't remember.
I saw you playing with numbers. You push the math button, then you go over to PRB and you'll find that NCR thing. But it's not that important that we get that number. But it is big? How big?
Like 6.867 times 10 to the, yeah,
6.87 times 10 to the
10th, I guess?
the 10th? Is it
E10.
E10? 10 to the 10th. So it's a lot bigger than a million. 10 to the 10th, a billion is 10 to the 9th. So that's 10 billion. So there's 68 billion, basically. 68 billion possible samples. I got 77 of them. Right? But there's another reason why this number, that number is a little too big. I'm sorry, why this number is a little too small. There's a reason why this number is a little bit too small, and that is because this number is a little too small. This is an underestimate of sigma. And every single semester, you get that number underestimates the sigma. And why do you think that is? And this is part of the discussion that I want to save for another day, because we're going to talk about confidence intervals. But just in a nutshell, this theory works if you use random sampling. Did you guys use random sampling? Use convenience sampling. So what happens when you use convenience sampling? What kind of people do you choose? People around you, people in your family, people that are all a little bit too much alike. Those 5 people are pretty similar people, which means your estimate of the standard deviation is going to be a little too small. You're not getting the total variability that you would get if you just randomly chose people, right? So we're underestimating a little bit what sigma is, which means this is an underestimate. So, again, we'll hit that a lot harder later on. Okay? Whoops, I don't want to erase all that yet. What this does then, I think I'm done with the projector. Let me shut that off. This gives us the basis of something called the central limit theorem. And this is actually section 7.3, which I'm not going to cover in its entirety, just to pick up that day that we're behind. And as soon as you see this central limit theorem, you'll realize, well, isn't that what we just did? And that's why I feel like I could skip that section, because yeah, we really already did that. The central limit theorem says, I'm going to start with sample means. There's 2 versions of this, one for sample means, one for sample proportions. For sample means, what the central limit theorem says is that x bar from a sample, I need to not just write a sample, from a simple random sample x bar from a simple random sample can I make one little change to this sentence? Yeah, I think you'll be able to fit it in. You don't have to erase anything. Just put a little apostrophe s. I want to emphasize that I'm talking about all of the possible x bars, not just one that you get. Okay? So x bars from simple random samples will have an approximately normal distribution. With mean mu sub x bar equal to what we said over here, equal to the population mean, which we call mu, and standard error of x bar will be equal to this. The population standard deviation divided by the square root of the sample size. Now I think you'll agree we've pretty much done all that already, right? I didn't say that it would be approximately normally distributed, but you saw it was bell-shaped and symmetric. Right? Now you might be thinking, now wait a minute, you showed us pulses, which come from a nice bell-shaped symmetric distribution to start with. So the means from that distribution is going to be going to have a bell-shaped and symmetric distribution. But what about like the ages? Remember how skewed that distribution was? What if I take samples from the age distribution and compute the mean of those samples? What is that distribution going to look like? Well, it turns out it will be approximately normal. So this theorem does not say that the x's have to come from normal distribution. It says the means, x bars, from those samples will be normal no matter what distribution x has. But it will be, it says, it's careful to say it's approximately normal. Now that approximation gets better and better as your sample size gets bigger and bigger. Okay? So it'll be approximately normal. N greater than or equal to 30 is a rule of thumb. For that distribution to be approximately normal. Now if you start with a normal distribution like pulses, you don't have to get n equal 30 before it becomes bell-shaped and symmetric. We saw it happen with 5. But if we did it with the ages, and unfortunately I didn't do it in advance to show you, but if I do it with ages, my sampling distribution from samples of size 5 would still be fairly skewed. Size 10, it's almost gone, the skewness. And by the time I get to size 30, then it's very bell-shaped and symmetric. Okay? Now you had this same idea of a minimum sample size when we did sampling distributions last time. So what I want to do now is give the central limit theorem for sample proportions. It looks almost identical to this, but you just make the appropriate changes. So for proportions, I'll call them props. P hats from simple random samples. I'm going to call those SRSs, simple random samples. We'll have an approximately normal distribution. With the mean of p hats equal to, you better not have forgotten this one because we just did it at the beginning of class. Where's the distribution centered? P. And standard error of p hat equal to square root of p times 1 minus p all over n. The central limit theorem applies to proportions and to means. And to other statistics too, but those are the two that we talk about in this class. It doesn't apply to every single statistic, but it applies to a lot more than just these two. I mean, you can compute medians, it applies to that. You can compute standard deviations, it doesn't work for that. Right? So it works for some summary statistics, not for others. But p hat is actually a sample mean. Think about, remember earlier I said code the no's as zeros and the ones as yeses? If I code that in my data set and I tell my calculator to compute the mean of that list of zeros and ones, think about that for a second. How do you compute a mean? You add them all up and you divide by how many you added, right? Well, if I got zeros and ones and I have a 1 every time I had a success, then when I sum that, I just get the number of successes. So I get number of successes divided by n. Oh, that's p hat. So p hat is a sample mean. So that's why the central limit theorem must apply to p hats just like it does to x bars, because p hats are actually sample means. Okay? So this is called the central limit theorem. Now I know what you're thinking. You're thinking, so what? Right? What do I care about all this stuff? Well, you care about it because your grade depends on it. I'm going to have to erase all this so I have a boardroom. But no, what we care about it for is because we need this result in order to do statistical inference. To make inference from a sample to the population, we need to know how close do we think our sample is to the truth. So I have a sampling distribution that's centered at the truth, but I don't know what the truth is. So I know it's going to be bell-shaped, and I know it's going to have a center somewhere, and I know that halfway down the hill it takes me out to 1 standard error, so that distance is sigma over the square root of n, so this is mu minus sigma over the square root of n, and halfway down the hill here is mu plus sigma over the square root of n. That's my sampling distribution of x bar. So from that I can compute probabilities. Suppose I think that the average income in 2010 is about the same as it was in the year 2000. I know what the average income was in 2000. Now I'm doing research to find out what it is in 2010. So I compute a sample, and I find out, lo and behold, that the sample income in 2010 is about 3 standard errors above what it was back in 2000. Does that mean that I'm using the word mean. Does that mean that the means has changed? Not necessarily, but what it tells you is, well, if it didn't change, then the result you got from your sample is highly unusual. It's 3 standard errors above the mean. So that's statistical inference. Okay? So let's take the few minutes that we have left and work a couple of homework problems that'll be similar to what you're going to do on the online homework. Problem 718 on page 332 is about New Zealand farm workers and their incomes, weekly incomes. And it says, from the population of farm workers in New Zealand, suppose that weekly income has a distribution that is skewed to the right, with a mean of 500 and a standard deviation of 160. So mu is 500, sigma is 160. They tell me those as population parameters. They're saying in New Zealand that's the case. A researcher unaware of these values plans to randomly sample 100 farm workers and use that sample mean x bar to estimate mu. Okay? Part A. Show that the standard error of x bar is equal to 16. So part A says standard error of x bar. Compute that. So how do I compute the standard error of x bar? Well, you take sigma, which is 160, divide by the square root of the sample size. Now they were nice to use 100 because that's a nice perfect square. So I can take 160 divide by 10 and I get 16. So they say show that it's equal to 16. So there you go. Part B says explain why it's almost certain that the sample mean will fall within 48 of 500. What is 48 within 48 of 500? Yeah. Only now we don't say standard deviations, we say standard errors. But it really is a standard deviation. So 48 is 3 of those guys. So the mean minus 3 standard errors and the mean plus 3 standard errors should contain what percent of all possible x bars? 99.7%, right? That's all or nearly all, right? So 99.7% of all x bars should be within 3 standard errors. Okay? Mariana, you had your hand up.
I missed what you said the question was on B.
You mean like what number in the book?
Part B, yeah, what did part B ask?
Oh, part B says, explain why it's almost certain that the sample mean will fall within 48 of 500. Okay? Then part C says to compute the probability, it says the sampling distribution of x bar provides the probability that x falls within a certain distance of mu. Show how to calculate the probability that x bar falls within 20 of mu. Hint, use the standard error, convert the distance to z-score, blah, 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 use the table in the back of the book. You don't need to do that. We've got to calculate it. What they want is the probability that x bar will be between 480 and 520. He says within 20 of the mean 500. So that means between 480 and 520. Now how the heck am I going to compute that probability? Normal one of them. It's a normal CDF problem. How do I know to use the normal CDF? Because the central limit theorem tells me that x bar will have a normal distribution as long as n is greater than 30. Is n greater than 30? We used 100, right? Sample size was 100, so I know I've got a normal distribution. See why the central limit theorem is important? Without it, we couldn't compute this probability. We wouldn't have any idea. So what do I put into my normal CDF function? Left and right. Well, here's my left, there's my right of the interval I want the probability for. So 480 to 520. Mean is 500. And the standard deviation, do I put 160? Hint? No. What do I put?
Standard error.
Standard error. Because the probability statement here isn't x. It would be 160 if this was an x, because that is the standard deviation of individuals. But the standard deviation, which we now call a standard error, of x bars is 16. So that goes here. So I'm going to put a big arrow there, standard error of x bar, not sigma. Okay? Be careful with that. Okay. 7.1 homework is due tonight by midnight. 7.2 homework will be due Wednesday by midnight. So we'll see you on Wednesday.